Welcome to Chem Help ASAP. Let's see an application of regioselectivity in electrophilic aromatic substitutions. The work in this video was performed by a team of scientists at Janssen R&D, a division of Johnson & Johnson in San Diego, California. The group was led by Dr. Michael Americks. The work was published in the journal ACS Medicinal Chemistry Letters. The citation is on the following slides as well as in the video description. On the screen, we have a reaction to the right. The starting material contains multiple aromatic rings. The benzene ring on the right is clearly aromatic. If we look at the rings on the left, both of the rings together could be aromatic. It's flat, sp2 hybridized atoms, and 10 total electrons, 4 pi bonds, and the nitrogen lone pair. Just the 5-membered ring could be aromatic, flat, sp2 hybridized atoms, and 6 total electrons, 2 pi bonds, and the nitrogen lone pair. No matter how you look at the starting material, there are many carbons that could participate in an electrophilic aromatic substitution. Regardless, when treated with an electrophile, just one, this carbon reacts. It's this one off the 5-membered ring. Why? When chemists discuss the reactivity of different aromatic rings, rings are often put into 3 main categories. We'll show them to the left. 1, there are the standard benzene rings. 2, we have the 5-membered rings, which contain an additional atom like nitrogen, oxygen, and sulfur. And then 3, again we have 6-membered rings which contain an atom in the ring like nitrogen. The 5-membered rings are often referred to as pi excessive rings because the 6 electrons for Huckel's rules are spread out over just 5 ring atoms instead of 6. In general, the 5-membered rings are more nucleophilic than the other types. That reason is why the Janssen scientists could selectively react the carbon on the 5-membered ring instead of the other atoms. Let's look at the mechanism. It's kind of a messy molecule, but the electrophile is over above the arrow, NBS, N-bromosuccinimide. Note that NBS isn't normally a good enough electrophile for an EAS reaction, but it works just fine with a more reactive pi excessive ring. The ring attacks to form a carbocation intermediate, which we show in the bottom middle of the screen. One of the ring nitrogens can actually help form a new resonance form, which we show on the bottom right, which stabilizes this cation intermediate. So we form a very stable reaction intermediate. Loss of a proton by a base, like maybe the counterion for our succinimide, push all those electrons back, and it gives us our final product. This reaction occurs with a yield of 87%. It works very, very well. The product from the reaction was carried forward to the molecule in the middle of the screen. This molecule is found to act upon neurotransmitter receptors with potential activity as an anticonvulsant. Further research, which relied on very similar chemistry, including the bromination with MBS, afforded the molecule to the far right. This molecule is JNJ, which stands for Johnson & Johnson, 614320059. It's a more potent anticonvulsant and shows promising activity in rats. In conclusion, the synthesis of a series of promising anticonvulsants relies on a regioselective bromination of aromatic rings. If you want to learn more about how the Janssen scientists prepared the molecules and studied their biological activity, then check out the reference on this slide or in the video description. Please subscribe, like, or leave a comment. Take care.